you so much for coming back to my channel, for joining me again to talk about some set theories. So, I hope you're all having a wonderful day. Sit back, relax, and let's get started. Okay, so what do we want to talk about today? So, in previous videos, I've talked about how there's a relationship between the intersection sign and the notion of and. And that makes a lot of sense, right? Because if we're talking about the intersection between two sets, A and B, we're talking about the region where both A and B are present. Likewise, there's a lot of connection between the union symbol and or, right? Because if we're talking about the union of A and B, we're talking about the region where either A or B is present. Okay, so today I want to go into a bit more detail about the connection between intersection and union and or. And what this brings into focus is the connection between set theory and logic. The key point here is that both set theory and statement logic, and also other applications like theories of electrical circuits, all of these notions are fundamentally rooted in the concept of Boolean algebra. So let's talk a bit about what that means and why all these systems are so similar to each other and so connected to each other. So let's get started.
Okay, so we are exploring the deep relationship that and, or, and not have with our set theoretic operators. So specifically, and has with intersection, or has with union, and not has with the complement operator. So let's start by looking at other kinds of mathematical systems which also make use of and, or, and not operators. And then we can see the connection that all of these systems have with each other. So let's get started on that. So if you've studied logic before, you've probably seen sentences of the form P wedge Q, where the wedge operator looks like this sort of upside down V. So what does that mean exactly? So in logic, we want to talk about when certain sentences are true and when they're false. So let's have a look at this particular sentence P and Q and see when it's true and when it's false. So when P is true and Q is true, P and Q is also true. But in any other circumstance, P and Q is false. So for example, if P is true but Q is false, P is false but Q is true, or they're both false, okay? In all of those other circumstances, P and Q is false. So the only circumstance in which P and Q is true is when P is true and Q is true. So that's what we mean when we write down this wedge operator here. So in this kind of statement logic, we have an operator which corresponds to and that is the wedge operator. The next operator we want to look at is statements that look like this, with an operator which looks something like a V. So let's try and see when this statement is true. So like the statement with the wedge operator, it depends on whether or not P is true and whether or not Q is true. So what we find with this P or Q sentence here is that it is false whenever P is false and Q is false. In all other circumstances, it's true. The statement P or Q is true whenever at least one of P or Q is true. So when they're both true, it counts, right? The rule is that at least one of them has to be true. So if they're both true, it counts. It's also true if P is true and Q is false, because remember, only one of them needs to be true. And then likewise, it's also true when P is false and Q is true, because again, only one of them needs to be true. So with regards to this operator here, it's only false when both P is false and Q is false. In all other circumstances, where at least one of P and Q is true, P or Q is true. So this kind of statement logic, we also have an operator which corresponds to or, and it is that the operator. Okay, the last one is whether an operator corresponds to not. So statement logic does have an operator like that, and it looks like this kind of sideways and upside down L operator. So the rule for not P is actually pretty simple. All it does is it flips the truth value of P. So for example, if P is true, then not P is false. If P is false, then not P is true. So all it does is flip the truth value of P. Okay, so we found that in set theory, we have correspondence to and, or, and not. We have intersection, union, and complement. In statement logic, we also have correspondence with and, or, and not, namely the wedge, the v, and the not operator. So that's not the end of the correspondences. We also have this and, or, and not distinction when we talk about circuits. So, for example, let's say we want to talk about a circuit when the current in the circuit goes from A to B, right? So far, that's pretty simple. But what if we put a gate in the circuit? So let's say we put this gate P in the circuit. We can think of P as something like a switch. So whenever P is on, the circuit is allowed to go through, right? Whenever P is off, the circuit isn't allowed to go through and the current doesn't go from A to B. So that's what we mean when we talk about circuits. So we can design circuits which correspond to our and, or, and not operators. So let's say that we are looking at the current flowing from A to B, but this time the current has to flow through two serial switches, P and Q. So the current starts at A and is supposed to flow to B. But on its way, it has to pass through these two switches, P and Q. So if we think about it, the current will only go from A to B if P is on and Q is on. So this kind of circuit, the serial circuit, is something like an AND operator, right? Because both of these have to be on. Another kind of circuit we can look at is, again, the current has to flow from A to B, but this time the shape is a little different. This time it forks. So it goes through the switch P up here, and then down here, it goes through the switch Q. Okay, so let's think about how the current flows along this kind of circuit. So if P is on, the circuit can easily just go through P from A to B. Likewise, if Q is on, the circuit can flow from A through Q to B. The only time when the current is interrupted is if both of these are off. So only one of these needs to be on. Either P could be on or Q could be on, but only one of them needs to be on. So in this kind of situation, we have an OR. So we can model the distinction between and OR with circuits, just like we can with set theory and just like we can with logic. The last kind of circuit we could look at is sort of the most simple one. So again, the current is flowing from A to B, and it has to pass this time through P prime. So P prime is just like P, except it is the opposite. So whenever P is off, P prime is on, and whenever P is on, P prime is off. So it's the opposite. It's the opposite switch to P. So what does this remind you of? So this kind of flipping behavior is just the exact kind of behavior we see with not. So in all of these cases, we have a correspondence to and, or, and not. So when we're talking about circuits, with and, we have that kind of serial kind of circuit. We also have that sort of forking circuit that we saw, which corresponds to OR. And then finally, we also have that P prime circuit, where P prime is the opposite switch to P, which corresponds to not. So in the world of circuits, we also have correspondences to and, or, and not. Okay, so why do we see the same kinds of patterns in these quite different mathematical systems? So the theory of these kinds of systems comes down to the philosopher George Boole, who was a 19th century mathematician, philosopher, and logician. And he came up with the notion of Boolean algebra. So if you've studied software engineering at all, you probably recognize the term Boolean, which represents true or false statements. They're called Booleans in software engineering. So what a Boolean algebra is, it's stripping all the detail away from those mathematical systems of set theory, of logic, of circuits, and bringing them down to their ultra abstract level. So all of set theory, logic, circuits, they all make fundamental use of this notion of Boolean algebra. So let's have a look in more detail about what a Boolean algebra actually is. Okay, so you can think of a Boolean algebra as consisting of a sort of limited set of ingredients. So the first set of ingredients are variables. So it is an algebra, right? And you've probably studied algebra in school where you saw statements like, 3a plus 4b equals c. So here we have variables. We have variables a, b, c. And in this kind of algebra, in this kind of numeric algebra, a, b, and c stand for numbers. So the concept in Boolean algebra is pretty much exactly the same. We have variables, like a, b, c, p, q, and so on. But in numeric algebra, these variables can stand for absolutely any number at all. In Boolean algebra, all of these variables can either stand for 0 or 1. So when we try to find the value of a variable in Boolean algebra, we're only allowed to assign the value 0 or 1. So that's what makes Boolean algebra quite different from the kind of numeric algebra that you learnt in school. The other ingredient for Boolean algebra is what we've seen already. So we have the operators and, or, and not. Now, these operators are symbolized or notated in countless different ways, depending on the mathematical textbook that you are looking at. But here we're just going to use and, or, and not, because it's kind of easy to remember. So let's get started in defining what these actually mean. Okay, so when we have a statement like P and Q, we know that P can only be either 0 or 1, and also Q can either be 0 or 1. Likewise, the whole sentence P and Q, that can only be 0 or 1 also. Okay, so what does and in Boolean algebra actually mean? What it means is give me the minimum value of P and Q. So let's try and think of the possible values that P and Q could be. Okay, so if P is 1 and Q is 1, the minimum value of P and Q is 1. But if P is 1 and Q is 0, the minimum value is 0. If P is 0 and Q is 1, the minimum value is 0. And if both P and Q are 0, then the minimum value is 0. So you'll notice the same pattern with the logical wedge operator, that we only get 1 when both P and Q are 1. Or is sort of the opposite. So or is the max value of P and Q, okay? So if we have P, we have Q, and we have P or Q. Okay, so if P and Q are both 1, then the maximum value of P and Q is 1. If P is 1 and Q is 0, the maximum value is 1, right? Because that's the maximum value. If P is 0, but Q is 1, again, the maximum value is 1. But if they're both 0, then the maximum value is 0. So again, we have the same kind of pattern that we saw with the logical OR operator, right? Where we only get 0, we only get false if both of them are false. The last one we want to look at is the NOT operator. So NOT P corresponds to 1 minus P. So let's try and think of what P and not P are. Okay, so if P is 1, then not P is 1 minus 1, 1 minus 1, which equals 0. If P is 0, then not P is 1 minus 0, which equals 1. So again, you're seeing that flipping behavior that we saw with the not operator in logic or the circuit. Okay, so just to summarize all this, if we have P and Q, we take the minimum value of P and Q. So the only way we're going to get 1 is if they're both 1. When we have P or Q, we take the maximum value of them. So if either one of these is 1, then P or Q will be 1. And then for not P, we go 1 minus P. So if P is 1, 1 minus P is 0. If P is 0, 1 minus 0 is 1. Okay, so by now we're familiar with these Venn diagrams to represent sets. So let's call this set A, and let's call this set B. Now, additionally, what we're going to say is we're going to try to give the value of 1 or 0 to two sentences P and Q. So let's say that P equals 1 inside A and Q equals 1 inside B, and otherwise they're 0. So for example, outside of those two sets, P equals 0 and Q equals 0. In this kind of crescent moon shape here, P equals 1 because we're inside A, but we're outside B, so Q equals 0. And then it's just the reverse. It's just the reverse in this crescent moon shape here. So P equals 0 because we're outside A, and Q equals 1 because we're inside B. And then inside this sort of almond-shaped region here, they both equal 1, right? Because we're inside both circles. So if we were to take the intersection of the two sets, we would color in the section where P equals 1 and Q equals 1. Where A intersect B, then P equals 1 and Q equals 1. So again, we're seeing this correspondence between intersection and AND. If we were to take the union, then we'd color in these sections here. So you can see the union is any area where either P or Q equals 1. So A union B is either P equals 1 or Q equals 1. So again, we're seeing a correspondence between union and OR. So now we kind of understand that there is this sort of deep connection between the set theory operators, the logic operators, and the circuit operators. So the serial, the forking one, and the prime one. So there's this deep correspondence between these three sort of representations of Boolean algebra. And what we'll start to notice is that the same laws apply to all three domains, and any domain which is founded on a Boolean algebra. So let's start looking at a few of these. So you probably remember the commutative rule when we talked about it in terms of set theory. So what was the commutative rule? The commutative rule said that A intersect B is the same thing as B intersect A, and A union B is the same thing as B union A. So commutative rule basically just says swapping okay. Okay, so we have some idea about why this holds in set theory, right? And if you want a refresh of that, have a look at my video on set identities. But now we want to show that it's also true when we talk about logic and circuits. So let's look at the circuits first, right? So the commutative rule for the AND circuit, for the serial circuit, says that PQ has the same functionality, the same flow of current that QP in serial does, right? Now let's try and think about why this would be. So say both of these were on, right? Say they're both on, then the circuit is able to go through both switches without trouble. But if either one of these are off, say Q is off, then the circuit is going to be interrupted. And it doesn't matter which one is off, and it doesn't matter whether it's the first one or the second one that's off. The circuit is just going to be interrupted if either one of these are off. It doesn't matter what order the switches are in. So this is showing that the commutative rule holds for circuit design for these serial circuits as well as for set theory. Okay, so here we have the OR switch. So the only difference between these two diagrams is that the order of P and Q have switched. So let's say that Q is off. If P is on, the circuit is still able to flow perfectly well. The only situation where the circuit will be interrupted is if both of them are off. If both the switches are off, then the circuit will be interrupted. But what you can see is that it doesn't matter. We get the same behavior regardless of whether we put the P on top or the Q on top. So it's showing that swapping is okay, that order doesn't matter as far as the AND circuit or the OR circuit. Now, you can probably see why. So remember that AND corresponds to the minimum value of P and Q. But the minimum value of P and Q is exactly the same as the minimum value of Q and P. Likewise, OR, which corresponds to the maximum value of P and Q, is just the same thing as the maximum value of Q and P. It doesn't matter what order P and Q are in, the maximum value is going to be the same whatever order they're in. So this is giving you some idea of how the commutative rule, the rule that says that swapping the order of P and Q is fine, and how that holds when we talk about logic, when we talk about circuits, and when we talk about set theory. So let's look in a little more detail at the notion of complements. So in set theory, we have the notions of universe and the empty set, right? So the universe is the set of everything, right? And the empty set is the set of nothing. We also know that A, whatever A is, it doesn't matter what A is, A union the complement of A, we get the universe. And if you think about that one visually, if this is the universe and this is A, so this is A's complement, the union, the total area will be the universe. Then at the same time, if we took the intersection between A and its complement, we get the empty set. And that makes sense as well, right? Because when we take the intersection, we're talking about the overlapping area, but there's no overlapping area between A and A's complement, right? So the overlapping area is empty. So when we're talking about logic, we have sentences which correspond to the universe and the empty set. So we could just write the sentence 1, standing for the sentence which is always true. And as far as the empty set goes, we could just write the sentence 0, which stands for the sentence which is always false. Let's see if we can find a correspondence between these rules. So say we've got a sentence P or not P. So if P equals 1, then this sentence will equal 1 or not 1. We know not 1 is 1 minus 1. So 1 or 1 minus 1, which is 1 or 0. And then we know that or is the max value of 1 or 0, which equals 1. Okay, so far so good. What if we had the same sentence, P or not P, but P equals 0? So now we have 0 or not 0. We know that not 0 is 1 minus 0. So we have 0 or 1, and then we know that or is the max value of 0 or 1, which equals 1. So regardless of whether P is 1 or P is 0, the answer is always 1. So P or not P equals 1. And just scrolling back up here, we can see a clear correspondence between the statement P or not P equals 1 and A or A's complement equals the universe. Okay, what about this rule here? Okay, so just a reminder, just write it out again. A intersects A's complement equals the empty set. So in logic, this would correspond to P and not P. So we want to see if it equals 0 or not and corresponds to this rule. Let's say that P equals 1. So if P equals 1, then P and not P would be 1 and not 1. So that would equal 1 and 1 minus 1, which would be 1 and 0. And then and we know is the minimum value of 1 and 0. And then the minimum value of 1 and 0 is 0. Okay? So far so good. What if P equals 0, then we get 0 and not 0, which equals 0 and 1 minus 0, which equals 0 and 1, which is the minimum of 0 and 1, which equals 0. Okay, so it seems that if P equals 1, then P and not P equals 0. And if P equals 0, then P and not P equals 0. So regardless of what P is, P and not P equals 0. So we can see a clear correspondence between these two rules. So A intersected with A's complement is the empty set, and P and not P equals 0. Now, just quickly, we can see the same correspondence with the circuits. So if we've got a circuit running through P and P prime, right? Say that P is off, then P prime has to be on. So the circuit will be interrupted here. Otherwise, if P is on, then P prime has to be off. So in that circumstance, the circuit will be interrupted here. So regardless, this circuit here, where we've conjoined P and P prime, is always going to be off. The current will never be able to flow through this circuit. So again, so P and not P always leads to off, 0, false, or the empty set. Okay, and then what about the or? So if we got P or P prime connected by this forking structure, then it doesn't matter. If P is off, then P prime will be on, and then if P is on, then P prime will be off. But regardless, the current will be able to flow through, right? Because if P is on, the current can go this way, but if P is off, the current can go this way. So this one, this kind of circuit, where we have disjoined P and P prime, where we have connected them with OR, is always on. So we always get 1 through or the universe, right? It's always on. So you can see the correspondence in the circuit world. When we conjoin P and its complement, we always get a circuit which is always off. And then if we disjoin, if we have this forking structure with P and its complement, we always have a circuit which is on. So in the circuit world, we have a corollary. We have a corollary with this rule here.
Okay, so that gives us an idea of why there's such a big connection between set theory and statement logic and other kinds of mathematical systems. Basically because they're all interconnected with this notion of Boolean algebra. So that's about it for me. Thank you so much for watching. If you like this video, please remember to hit like and subscribe, and I'll see you next time to talk about some more set theories. So until then, bye everybody.